Hey, it's me, Steve. Today's topic, I'm going to talk about, some of you probably saw this in my last Geo-Rant. This rock I did, I think it's Geo-Rant number 55, I'll link to it below. But this rock here is not a land porphyry. It's not. I actually found out what outcrop it's at, and I want to talk about its origins and placement in more detail. And there it goes on the desk. But after I do that, because it's not going to be long enough, there's something, I'm hoping this works, there's something I want to show you. It's kind of cool. It's a collection of mine, but it's a special collection. But I'm going to have to wait until it gets dark out to do it. Oh, hello, Becky. Okay, so, alright, we are going to talk about this rock right here. I said I thought it was a land porphyry, but it's not. I was able to use the QAT PF Diagram to classify it. That's the quartz, alkali feldspar, plagioclase, feldspathoid igneous classification of rocks. It's just abbreviated QAT PF, and then it'll be diagram. But anyway, so you can look that up. You can Google that, and you'll see it's a two triangle type thing. They merge. They're like this. The stuff up here is for coarse grained. They have a fine grain and a coarse grain version. I obviously use a coarse grain for this. The rocks above this line, they have quartz in them. The rocks below this line have feldspathoids in them, or phoids. The reason why there's two triangles is because these two things cannot form together. If quartz forms, there's none of this. If this forms, there's no quartz. Okay, so I hope you can see it. I tried to print as clear as I could. Here's Lake Superior. This is Ontario. Here's DUP. This is the location. Here's Trans-Canada 17. Here's Ontario Route 101. You see 129 here, but it actually extends down this way. It just doesn't show up. And as you zoom in, that's the location. You zoom in, you can see here's 101. And then you zoom in more, it's at the junction of Ontario. It's just southeast of the junction of Ontario Route 101 and Ontario Route 651. The scale's right here. This is about a mile. You can barely see it. So it's not even a mile from it. And in case you couldn't see any of that, here's the GPS location in big, huge numbers. This is the outcrop looking west, southwest. There's actually a borderline between two townships there. There's Serapis Scale. So that sign is right there, but the rock was on the opposite side of the road. This outcrop is on both sides of the road, but I mean, if you get that GPS location, you can find it. All right, here we have, I called it in my notes a pegmatite, and I noticed this vein. I just didn't concentrate on it because I was actually focusing on the host rock, which here there's a picture of it. And the host rock, mineralogically, is very similar to this dike. It's just this dike is pegmatitic. All right, and there's tunies for scale there. And here's the dike of what I called the pegmatite, and here's the host rock, and here's a close-up of the host rock. The host rock does have a lot of hornblende in it, though, which is something that the hand specimen that Sarah picked up doesn't seem to have very much of, if any. But I did do a detailed analysis of this rock, which I'm going to get into in a moment. But the Other thing, this side that Sarah's standing on, actually it's right here. I almost missed it. There's a black dike running through there. That orange pencil is about 6 inches, so this isn't very wide, and it's likely Keweenaw. And just as a side note, it's black basalt, and it shows columnar joining, which is perpendicular to the intrusion direction. But that's just a nice little side note of something, but that's not the focus of this, but I just thought it was cool that there's some Keweenaw dikes there. All right, you can see this up here. I said in my Geo rant that I was going to do a detailed computer analysis of that rock, and I'll show it to you in a second. But what I want to show you is a detailed QAT PF diagram. This is the double triangle thing I told you about. Remember, from here up, if there's quartz, there's not going to be any feldspathoids, and there is definitely quartz in this rock, which I'm going to get into how I classified it in detail here. Okay, so here it is. This is to scale. This diagram right here is this rock face to scale. All right. So 1 inch here, that's physically 1 inch on here, and it's also physically 1 inch on this, and this is the face that was studied. Now, when you look at this, you'll see I have P, Q1, and Q2. P is my plagioclase, and I was right. It is anorthite. I have Q1 and Q2 for quartz. It's still quartz. It was just easier for me to kind of separate it because I was kind of questioning what Q2, if that was quartz or not, but I looked at it in detail. It is. So M is mica. In this case, it's biotite. All right, I was able to determine that under hand lens too, which my initial guess is right. And the A is for pyroxene, and here I have a question mark, augite. I believe it is augite. It's definitely pyroxene in some of the ground mass. The ground mass is two things. It's either this biotite, or it's this pyroxene. And basically, what is ground mass? Ground mass is everything that's in between all these grains. So these letters here correspond to these letters on this here. And you'll also notice on the very bottom I have monzonite, and then over here I have basically everything, and I just called it the zone because it's finer grained here. This rock is a pegmatite. It's pegmatitic. That means it has large, huge grains. Obviously, that's the anorthite right there. But this is just a little bit of monzonite from the host rock. This is part of the host rock right here. Over here is just a QAT PF diagram, small scale. It's written tiny. And here's what I decided to call it. It's a mafic porphyritic tonalite. Porphyritic just means big, huge chunks like pegmatite. But this does exist in a dike, as you saw in the picture. So that's what I finally decided to call it. And what's all this stuff here? Well, these black percentages are the percentages of volume of the rock. Basically what I did here, the reason why I did this is so I could basically calculate area of all the different rock types in order to get these percentages, and they're accurate to about plus or minus 1%. So those black percentages are all actual percentages of volume of the rock. I'm counting area here. The red percentages, now in order to calculate what type of rock this is, you have to remove the mafics. The mafics, if they're less than 90%, you adjust your percentages with those removed. In this case, we have two mafics. We have the biotite and we have the pyroxene, okay, which is actually pretty good percentage of the rock I'm removing here in order to classify this, but that's the way the QAT PF diagram works. They're not calculated in with it. I also removed the monzonite because it was such a small percentage to begin with, and the same thing with the zone. So these red percentages are my adjusted ones, and you can actually, here's the calculations in order to figure out how to adjust the percentages. So, and there's the rock name again on the bottom. So that's why I came to the conclusion that this thing was a tonalite. Now, the thing with tonalites is when we look at a rock like that, like this, we don't think tonalite. We just don't. The host rock is more conducive. It's actually a migmatite. And what a migmatite is it's a rock that's undergone so much heavy metamorphism that it partially melts. Now, some people sit there and say migmatite should be a fourth type of rock. I don't see the point of that. You can call the metamorphosed parts metamorphic and the melted parts igneous. You don't need a different rock type just to combine two other things. I mean, we don't do it with sedimentary rocks that have intrusions in them, so it just defeats purpose. But anyway, this is what we think of, because you can tell that the host rock here, it looks a lot like a pegmatite. It's got a lot of mafics in it too. That's what all that black is. The gray, and then you see the white, which is plagioclase as well. So this is kind of what we think of when we think of tonalite. We think of a rock like this, and that's a toonie on the bottom. We don't think of something like this. Now, I'm going to go through the origin of this and how I think this developed. Because, I mean, now that I remember the outcrop and found the outcrop that it was at, now, this is a very geologically complex area. Blackie, you doing some geology, buddy? All right, I drew the outcrop area for you, like the map I showed you earlier. The outcrop is not this big. I exaggerated it for clarity, but here's the name of the two townships that meet, and that little X is the spot where that sign in that picture was. So that's now the name of the outcrop. It's never been named before, so I decided to name it. Don't ask me how to pronounce it. But what I did here, I actually think I had it backwards last time. The sign is actually on the west side of 101. And that this is the strike and dip of that black Keweenaw dike. Now on the other side, this black squiggly line, that is about where the dike of the rock we're studying is located. So this black squiggly line is roughly the trend of the dike that this rock came from. So what can we infer from this outcrop of what's going on here? Well, like I said, the two blue circles here, that's the main host rock. That's that plagioclase-rich migmatite. The origin of the rock is likely igneous, and it's likely a tonalite, like the dike is. But we can't know for sure. It is really highly deformed. There's, like I said, there's also hornblende in the host rock, which was not in the dike. Well, obviously the dike formed later. This is the approximate trend. I didn't actually measure it, but it was about north-south-ish. From all the geologic maps I saw, I didn't see any faults in the area or anything, at least not known ones. Although our dike may actually be a shear zone. I've talked about shear zones before. That's where faulting happens during metamorphism, usually laterally, like, you know, it would be this way or that way, but the compression and heat is so intense that you can actually get melting. And that's what I think was going on here. I think whenever this host rock was metamorphosed at a high temperature, that we might have had some shearing going on. Now the rock at this outcrop weathers red, but it's plagioclase. There is some quartz monzonite in it. There are some pink parts, which quartz monzonite has a significant amount of alkali feldspar, but 99% of the host rock is not that. It just weathers red on the surface. But anyway, so what I think happened is while this is being deep underground and being metamorphosed, that this minor shear zone formed, and as the rock was churning and near that melting point, that you actually got melt out along this zone of where it was pushing. And if we follow Bohn's reaction series here, Now the host rock, since the dike is very similar to the host rock, the dike obviously originated from the host rock. And that augite, that white crystals in the rock, that's a calcium plagioclase. That would have crystallized first, forming those large white crystals you saw in the rock. At about the same time, the pyroxene would have started to cool out. And the pyroxene, this rock here, the pyroxene is basically from here down minus the monzonite. From here up, the ground mass is all biotite. And it was hard to determine that, but a hand lens was good enough because this rock is very coarse grained, as where the host rock is only medium grained. So you would have got that's how you ended up with the large white crystals, because they would have crystallized out first. And the fact that they had that red rim around them, which I actually touched on in that Geo rant. See, there's some red rims here. This tells me that as this was crystallizing out, the rest of this was still magma and was probably moving around and re-melting some of them. That's why they have, I believe that the red are actually baked zones. So you had the augite crystallizing, being moved around, whatnot, and the temperature of the rock lowered enough for where pyroxene could start to form, and then it probably started cooling a lot quicker. Now you would have had, at this point, you would have, these are already solid crystals, so whatever's left in that magma, you can only crystallize out chemically whatever's left in that magma. So the pyroxene started, but it's only medium grain. So the crystals didn't get as big as they did here. So initially, this, what I think is a shear zone and the melting along it, was around for a long time, long enough to form large plagioclase crystals, but then started to slow and stop moving as the pyroxene formed out, and then the biotite, and then the last thing to crystallize out is the quartz. Now the quartz is coarse grained, so this stuff was still kind of hot. But it's not huge crystals. It's not huge crystals of quartz like it is with the plagioclase. Okay, this chart here shows you kind of the progression and the temperatures needed to form certain types of minerals. Now, like, pyroxene is not an actual mineral. It's a group of minerals. Same thing with amphiboles and biotite, but they're all pretty much very similar. That's why they're grouped here. Now, we had a coarse-grained rock. Now, first thing to crystallize out, and they are the biggest crystals, would be our calcium-rich plagioclase feldspars, which in this case was the anorthite. So, right at the same time, and the pyroxene, like the anorthite, started to form, actually probably more like over here, because the crystals got pretty big and then the temperature lowered enough to start getting pyroxenes here. So we're talking about temperatures at 1,000 to 1,200 degrees Celsius. So we had that magma for a while, and then it seems to have cooled a lot quicker. We should have amphiboles, but we don't, which means chemically the elements needed to form amphibole just were no longer in that magma. So we didn't get any more crystallization until it got right about here. That's what this yellow line is. And we started to get biotite out of it and quartz. The biotite and quartz are somewhat large crystals. So we started at a magma of about 1,200 degrees Celsius, 1,000 to 1,200, and then it seems to have cooled rapidly down to maybe about 800 to 850 degrees Celsius, and we got our final crystallization. So that shear zone must have stopped shortly after we got our plagioclase and our pyroxene, and then it just started to cool until these other minerals could form out, and that's why we end up with the rock the way we did. we ended up with the largest crystals being at the highest temperature, and then the smaller ones, except for the pyroxene. I said the pyroxene didn't form large crystals. So the cooling right when the pyroxene started, so we started forming the augite, it was probably hot for a long time, didn't have the minerals to make olivine, or the elements. So we got the pyroxene, and as soon as we got the pyroxene, it probably just cooled rapidly. And then that allowed for the others to form, but this thing was still so far underground that instead of cooling just to a solid immediately, because the migmatite, the nature of a migmatite under lots of pressure, lots of heat, the whole rock being close to the melting point, we got rapid cooling at pyroxene, and then we hit this here and it just couldn't cool off anymore. So it started to crystallize large crystals of biotite and quartz. So, and then after that, at some point in the future, the migmatite totally was no longer under high temperature and high pressure and just cooled down in general. Now remember, you can still heat rocks without melting them, but the dike, or the shear zone that produced the dike, was definitely melted. So I just wanted to show you that. And if you look here, we have, it says granodiorite here. I'm going to show you something about that. Okay, so after our, what I assume was an Archean tonalite was emplaced, during the Archean as well, we got the deformation, the migmatitic conditions to get our dike and our probable shear zone. That's all likely Archean. This all likely happened in the Archean. But much later, that black basalt dike, here's the strike and dip, that's the red here. And that is not deformed at all, shows columnar jointing, and it's likely Keweenaw, so around 1.1 billion years old is where the rest of the rock was probably deposited around 2.7 billion years, and then metamorphosed 1, 2, 3, 4 times up until probably about maybe 2.5 billion years ago. We just don't know. So that's what I think was going on with the rock, the dike I showed you, the pegmatitic rock sample. So that I just wanted to do this for you to show you how you can take a simple rock, look at its mineralogy, figure out chemically what was going on here, and plot it, do some investigative work. Now this is just a rock. This doesn't tell me really any origins. Now these type of rocks can form in different environments, but when you combine it with the surrounding rock, you can get a better picture. You got to zoom out. So when you take this is your zoom in, and then you zoom out to try to get a geologic picture of what was going on here at this outcrop. Now, like I said, this whole area here has a long history of igneous metamorphic events, and even though this rock turned out not to be a land porphyry, there are land porphyries here. And this area is known for gold deposits, and also some diamonds to a lesser degree. So I think that sums it up for this part of this episode. But I've still got a little time left, but when that sun goes down, I have more than enough time to show you what I want to show you. Back to the QAT PF diagram I showed you earlier. I just showed you this. You may have noticed that right there. That's where our rock specimen plots, and as you can see, it's really close to granodiorite. So that's, if we move all the mafic minerals, like I explained before, that's where it plots really close to the line. I believe it was 91% plagioclase when adjusted for the removal of the mafics. So I just wanted to show that to you, to show that that's why it says granodiorite on that other chart I just showed you, and the cooling sequence. Instead of tonalite, you could put tonalite on there, but since the two rocks are so similar, most people just write granodiorite. They don't write granodiorite / tonalite on that chart. Okay, it's just shy of 2100, so it's dark enough out, and there's something I want to show you. Look, rocks. Ooh, Steve, you have tons of rocks. These are special rocks, and I'm going to show you why, and I hope the camera, since I'm using my phone, will pick this up. But I'm going to show them to you first, and then I'm going to turn the lights up. Blackie is posing for scale. He's probably the largest domestic black cat on the planet, so he's not a very good reference, but you can see some of these rocks have stuff in them, like there's micas in this one. You can see some are anhydrites, there's some fluorite. I'm not going to go into too much detail. There's more fluorite, there's hornblende in this one. Now there's some more down here. Yeah, I'm not, like I said, I'm not going to go into too much detail on them. That's a rant for another time. But there's something I'm going to show you. Okay, it's dark out right now, so I hope this works. Alright, I have a black light, and here it is in short wave. As you can see, the rocks are fluorescing. I have to get it pretty close for the camera to pick it up, but it is working. These are the rocks on top of the desk. Some of them fluoresce really well, you just can't see it on the camera. But the one with mica is not that good. But this one, I love this one right here. And that one too. More oranges. Now we're going to do the ones on the floor in shortwave. You can see some specks. Nothing really flashy. I've organized them into highly fluorescent and not very highly fluorescent. The ones on the floor really don't. This one, I wish you could see. You can kind of see it. It's glowing orange in part. I believe that one's... No, it's not what I thought it was, but... yeah, the camera doesn't do it justice. And this one, that one's really good. Real bright orange. Now, let's do long wave. The ones that don't fluoresce on the bottom very much. I'm still on the floor here. Now some really fluoresce in long waves. Some of the really ones like this one right here in the middle, in the short wave, you could barely see it. Now it's a lot better. So, but the bright oranges, notice you don't see really the bright, you see the little ones in the bag, the yellows. But, and my paper. So, short wave, right there. Long wave. These are the ones on my desk. So I hope you enjoyed that little demonstration there with the black light to show you how some rocks can fluoresce and fluoresce pretty brightly. The video wasn't as good as it looked in real life, so I took a couple pictures. I'll post, they'll be in the credits. So I just hope you enjoyed that. I used this lamp. It's a Raytech ultraviolet. It looks like it's from the 60s. Model LS7-AM35. It has two settings. The long wave up top, which is this bar, and the short wave, which is this bar. And it hums in the short wave. Doesn't really hum much in the long wave. But I've had this for a long time in these rocks, and I hope you enjoyed that because it's really cool. And also, I hope you learned something today.